Thermochemistry. So as usual, I picked out some out of the review document, highlighted them. So those are the ones we're going to work with today. Start with number 2. What's the kinetic energy of 1.56 kilogram object moving at 94 kilometers per hour? Seems straightforward. I mean, if you're going to calculate the kinetic energy of an object, you're working with this formula. And so you need to know the mass, you need to know the velocity, but these have to be in SI units. This has to be in kilograms, which it is 1.56 kilograms, and the velocity has to be in meters per second. Right, meters per second. It's not in meters per second. So 94.0 kilometers per hour. We need to convert that to meters per second. So we're back to dimensional analysis again. And remember, when you have 2 or more units that have to be converted, do one at a time. So I'm going to take kilometers first, convert it to meters. Kilometers on the bottom to cancel, meters on the top. So how many meters in a kilometer? 1,000. 1,000. Okay, got that taken care of. Now we got to convert hours to seconds. Okay. Hours on top, so it'll cancel. Seconds. Does anybody know how many seconds are in an hour? If you don't, then you can chain them together. Right? We know how many minutes are in an hour, right? 60 minutes. So we got rid of hours. Now we got a minute we got to get rid of. So minutes here and seconds here. So how many seconds in a minute? 60. Okay. So in the future, 60 times 60 is 3,600. 3,600 seconds in an hour. And then we just, that's the thinking part. For this part of the experiment. Answer the question. This will give you the value that goes in here, which must be squared, and then times kilograms times a half, and that gives you energy. The reason that we have to have these standard units of measure is because if we don't, then the answer will not come out in joules, and that's what we want. Okay, so let's find out what the velocity is. 94 times 1,000 divided by 3,600 is 26.111. 26.11. I like to keep decimals until I can throw them away. Meters per second. So that's going to be this term, and then mass is going to be 1.56 kilograms, and then times a half. So I've got that one in my calculator already. I'm going to square it. I'm a square key. There it is. And then times 1.56, and then take half of that. So I get, my calculator says 7963 joules. But we've got 3 significant figures here and 3 here, and we've only had multiply divide. So we just need to look for the smallest, the least number, which is the same for both of them. So we need to round off to 3 places. 1, 2, 3. Is our answer in joules? No, it's in kilojoules. Okay. All right. So how many joules in a kilojoule? There's joules. 10 to the third joules in a kilojoule, right? So this is 532. It'd be easier this way. 532 times 10 to the minus 3 kilojoules, right? Because it was in the denominator here. In the numerator, change the sign. But we want it in scientific notation. So we move it 2 to the left. That's 100, or 2, it's like this, 5.32 times 10 squared times 10 to the minus 3. Okay, so this together equals the -1. Right. 32 times 10 to the -1 kilojoules. There you go. So that one is turning on first. Hey, right there. Yep. Now, why did we do a physics problem in chemistry? Well, physicists will tell you that chemistry is just applied physics. Right? And there's a whole branch of chemistry called physical chemistry. That's all they do. They treat chemistry as if it's just a bunch of objects bouncing off each other. And that is when they're doing the research. I mean, when they're in classroom, their sole purpose is to torture students, right? From personal experience. Which of the following statements correctly describes the signs of a Q and W for the following exothermic process? Okay, so we know it's exothermic. That means, let me just write it up here. So it's an exothermic process, and we've got, well, actually, we could probably figure this one out. If we go from gas to liquid, it has to be exothermic. You got to release energy from this gas to make it liquid. Okay, what else are we given? 1 atmosphere. 1 atmosphere. That's supposed to be an equal sign. That should be an equals. That should be an equals. Temperature equals 370 K. Okay, so signs of Q and W. Okay, so what's Q? Q is the heat transfer, isn't it? Yeah. Heat transfer. And exothermic, everything is in relation or reference to the system. So if it's exothermic, heat's leaving the system. So that means that this has to be negative, right? Okay. But with a gas, I like to look at it this way. If this is under constant 1 atmosphere pressure and the temperature is constant, then as a gas, say it fills this space. And then when it condenses, what's it going to do? It's going to turn into a liquid that's probably 1,000th of the volume of that gas, roughly speaking. So we got a little bit of liquid at the bottom. What's left? Vacuum. So plus maybe a few gas molecules. So it's going to go down. So in reference to the gas, the surroundings are doing work on the system. Because the outside is the surroundings. And if this is moving down, a force is being applied through the distance on the system. So work has to be positive. All right, so it should be this one. Okay. This one's easy to do. This one may take some mental gyrations to understand it. Get comfortable with it anyway. All right. Let's see if I can do this. We got to split. So just like that. 7. 1 mole of an ideal gas is expanded from a volume of 1 liter to a volume of 8.93 liters. So let's see, we have a gas, 1 mole of it, and its initial volume is 1 liter, right? Very significant figures. And it expands to a final volume of 8.93 liters. Okay. The pressure is constant at 1 atmosphere. 1 atmosphere. Okay. how much work in joules is performed on the surroundings? Is that true? If it goes from 1 liter to 8.9 liters, it's expanding against a constant pressure. Okay, that's true. It's working against the surroundings, so it's W would be negative. So how much work is performed on the surroundings? Okay, we're looking for this. P delta V. There we go. That's the formula we're looking for. So this should give it to us not in joules, but in liter atmospheres. So what's delta V? It's final minus initial. So we got this 1 atmosphere. And then we got final minus initial. Okay. So the work in those units is 8.93, isn't it? Negative 8.93 liter atmospheres. So we got to convert it to joules. And 1 liter atmosphere is
Should
equal
be
to
8.93 minus 1.0, should be 7 point.
yes, thank you. Most of my classes just let me roll on.
I don't always
Thank you. No, I'd rather have it that way. The last thing I want to do is confuse the class. That's right. That's what it should be. 793. Now we need to convert that to joules. And we have our equivalents there. 1 liter atmosphere equals 101.3 joules. So minus 7.93 liter atmospheres. We're going to convert that. Liter atmospheres down here, joules up here. So 1 liter atmosphere is 101.3 joules. So that's what we need to do. So 100 times that is about 800. It's probably be 803.
Be negative 803.
Thank you. Okay. Well, calculate the work associated with the compression of a gas from 121 liters. So initial volume is 121.0 liters. Final volume is 80.0 liters under a constant pressure of 13.1 x. Pressure is constant at 13.1 x. Okay. Oh, this is nice. They let us leave it in liter atmospheres. So all we have to do is take constant pressure atmospheres. And then final minus initial. Okay. And so that's going to be a minus 41 times 13.1. And it's a negative sign, so we change the sign. And we've got 3 significant figures. 537 liter atmospheres. Positive. And that fits because the surroundings are doing work on the system. B. Okay. 14. 14 is 14 through 17, I don't know if I do all of them. Yeah, I probably do. It's based upon that first statement. Consider a gas in a 1 liter bulb. So volume equals 1 liter. Got a gas in this 1 liter bulb. Okay. At standard temperature and pressure. So what's standard pressure? 1 atmosphere. Temperature. Well, I'm not sure which one they want us to use. I think when we're just doing gas calculations, the standard is 0 degrees C. But they could be 25 degrees C. That's a problem. Which one is which? As long as it doesn't change, we're okay. It's connected by a valve to another bulb. There's your valve connected to another bulb. It doesn't tell us what the volume is. It just says that there's a vacuum in here. Okay, now, when you open the valve, what happens for 14? What happens to Q? Right. If it's constant temperature, there's no transfer. There's no heat transfer. So Q would have to be equal to 0. How about 15? What's 15? Work. W equals what? Well, 1 atmosphere is, 1 atmosphere is in here. So the pressure decreases, but it's not moving anything. It's just the gas is filling the space. It's not working against the it's still internal, right? This is in the system. Surroundings have nothing to do with it. So we can't calculate work that way. It's 0 also. 16. Here we go. How about delta E? All right, what's delta E? It's Q plus not G, Q plus W, right? Well, we already determined those are 0, so this has to be 0. Okay. And the last one, 17, delta H. What's delta H? Delta H is enthalpy. The only time that it's equal to Q is when the pressure is constant. And that is the pressure between the system and the surroundings is constant. And the surroundings have no influence on this whatsoever. So since we found that one to be 0, this one's got to be 0 too. So they're all 0. Uh, 18. Let's scroll back. Yes. Maybe it'll work. 18. Energy, work, enthalpy, and heat. How many are state functions? Oh, I left the highlights here. Yeah, bolded, yeah. All right, so we've got energy, work, enthalpy, and heat. The only state functions in there are these two. These depend on the path. I don't have a good explanation. That's one of those things you just have to take on faith. We don't have time to go through thermodynamics right now. We get that next semester. Great. 19. Which of the following properties are intensive properties? Okay. So an intensive property means that no matter how much of the stuff you have, the value is still the same. So how about mass? No, you get more stuff, you got more mass. Right, so one can't be it. Right, one's not it. How about two? Temperature. Aha. As long as it's equilibrated throughout the entire substance, then the temperature, anywhere you measure, it's going to be the same. That is an intensive property. Volume. No, you got more stuff, you got more volume. 4. Concentration. Yep. It's a so many things for mass per unit. Something volume usually. So if you have a solution that's 1 molar, like 1 mole per liter, if you only have a half of that liter, you still got 1 mole per liter. So yeah, that one's true. And energy. No. Energy rises and falls with the amount. So there's only 2 of them, right? 2 and 4 are intensive properties. Let's see, 23. So we got this reaction, kind of hard to read. That's ethanol, the drinking kind, and we're going to burn it. We either burn it in a flame or we drink it, and our body does this to it eventually, but in smaller steps so that we don't burn the cells up. Right? We make carbon dioxide and water out of it. And this is the amount, this is the enthalpy of that reaction. So it's exothermic. Okay, consider the following propositions. The reaction is endothermic, the reaction is exothermic. The enthalpy term would be different if the water form was gaseous. Okay, we know that 2 is true. It's exothermic because delta H is negative. Okay. So Roman numeral 2 is true. Roman numeral can't be both. So 1 is out. But what about 3? The enthalpy term would be different if the water formed was gaseous. We've got water to liquid. Yeah. Because this reaction produces a lot of heat. Think of it this way. It makes a lot of heat. So if you had a alcohol candle and you held one of your test tubes over it, it would fog because it has water vapor in it. But the water vapor condenses on that cold tube. So if it condenses, that means it's giving up some more heat when it does that. So this incorporates that condensation energy. So if this was gas, there wouldn't be quite as much energy. Oh, well, actually, there would be more energy. Right? Because that means that you wouldn't have to give up any of that energy to condense it. So yes, 3, the enthalpy term would be different. 2 and 3 are both true. So that's E. So we're still mixing chemistry and physics. Let's see. Yeah, then I can page to the next one. 24. How much heat is required to raise the temperature of 5.75 grams of iron? 5.75 grams of iron. So that's the mass. Specific heat of iron is 0.450 joules per gram degrees C. Okay. And the temperature change, what's the initial temperature? 25. Okay, and we're going up to 79.8. Final temperature. Okay, so what's the formula we need? This is a fairly straightforward problem. Calculate the heat change. Q equals S, specific heat, times mass, times change in temperature. Y'all gonna be using that one a lot today. Okay, so all we have to do is plug in the values. I'm gonna leave off the units because it takes too long to write them. 5.75 grams. And this is, we have to be sure that the units are correct. That's grams, that's grams. So it cancels the grams. How about the temperature? Final minus initial. Degree C. So degree C in the numerator cancels the denominator. These two are canceled, we're left with joules. That's good. So if we do the calculations correctly, we should get 142 joules. Right, and that's positive. Because the system is the chunk of iron, and we're adding heat to it. So this should be positive. Oh, I didn't throw a negative at you. If I were sneaky, I'd put a negative one in there too. All right. 26. 32.5 gram piece of aluminum with a molar heat capacity of that value is heated to 82.4 degrees and dropped into a calorimeter containing water. Specific heat of the water is that, initially at 22.3. Final temperature of the water is 24.2. Calculate the mass of water in the calorimeter. Okay, that seems like a monster problem. It's got a lot of information in there, which I find is easier to extract the information and put it in some form of tabular so you can make sense of it. So we've got a mass of aluminum at 32.5 grams. Mass of aluminum is 32.5 grams with a molar heat capacity. I'm gonna put, no, it's not right. Need another symbol for molar heat capacity. Something like that. To be different from the heat capacity due to mass, 24.03. Joules per mole degrees C. Okay. We're gonna, it's heated, its initial temperature. So the temperature, the initial temperature of the aluminum is 82.4 degrees C. What's the final temperature of the aluminum?
22.3.
22. Let's see. 24.2. Yeah, 24.2. Okay. So that takes care of the aluminum. And we're dropping it in a calorimeter with water. Okay, so now we got water. So what we want to know is the mass of the water. That's our unknown. Specific heat of water is 4.18 joules per gram degree C. And the initial temperature of the water equals 22.3 degrees. And the final temperature of the water is 24.2 degrees. There we go. Okay, so I think that's everything we know. And we're ignoring the heat capacity of the calorimeter. They don't say that, but you have to, because it's not given. So what are we going to do with this? Well, everything that happens in Vegas stays in Vegas. It's zero. All these heat transformations have to equal zero inside the calorimeter. So let's do the water first. So this is going to be the heat for the water plus the heat change for the aluminum. And the heat for the water is going to be the specific heat of water here times the mass of the water, which we don't know, times the change in temperature. So the final temperature of water is 24.2 minus the initial 22.3. Okay. Then we're going to add whatever the aluminum does. So the aluminum, okay, we got a problem. We're given 32.5 grams of aluminum, but the specific heat is in terms of moles. So how do you deal with that? Convert this to moles. Okay. 32.5 grams of aluminum. So we need what? Molar mass. And this room doesn't have periodic table in it. Of course not. So I gotta look at it. It's 26.98. I was close. There we go. Now we find out how many moles of aluminum we have. Let's go ahead and do that. 32.5 divided by 26.98. So that's 1.2046 moles of aluminum. Now we can do it. So the specific heat, the molar heat for aluminum is 24.03. Okay. And the moles of aluminum is 1.2046. And then the change in temperature is final, 24.2 minus 82.4. There we go. So now what we have to do is do some number crunching and solve for that value. Okay. Not sure how much any more I have to do. But I need to spend time on this one. Because I gotta be done about 145. Would it, you have trouble doing this type of calculation? Okay, I'll do it. What's the change in temperature here? 82.4, 24.2. But that's a minus. Right? That's a bigger number than this, minus. So that's minus 58.2. Right there. That times this times that. And 24. So this value right here, this term is a minus 1684.7 joules. This term is, I should be able to do that in my hand, but I'm too hot right now. 1.9. That's 1.9 degrees C difference there. Times 4.18 is 7.942. So these two together, 7.9420. And then all together, that's mass of water. Okay, so we got this negative value over here. If we bring it to this side of the equation, it's a positive. 0.7 equals, right, because that's a plus, this is a minus, is 7.9420 times mass of the water. So the mass of the water is just this one divided by that one. And since the sign changed, we don't end up with a negative mass. That's good news. Okay, so let's see, divide. 212. Yep, 212 grams. There we go. Right, 26. If you get really wrapped up in the looking down the road to doing the heat calculation might miss that transformation from mass to moles. That would be, my guess is there's one in here. They need to
The one
take that into
answers
account.
Yeah.
So you'll find your answer, but it's the wrong one.
Mhm.
Okay, 27. And 28 together. All right, 45.9 gram sample of metal is heated to 95.2 degrees and then placed in a calorimeter containing 120 grams of water. At 21.6, the final temperature of the water is 24.5. Which metal was used? Right, so the unknown is going to be the specific heat of the metal. So we've got the mass of the metal equals 45.9 grams. Initial heat temperature is 95.2 degrees C. Final temperature is the temperature of the water at equilibrium. It's 21.6, right? No. 24.5. That's the final temperature. And we don't know what this is. The mass of the water, this is the metal. Mass of the water is 120 grams. And the specific heat of water is 4.18 joules per gram degree C. And initial temperature of the water is 21.6 degrees C. And the final temperature is the same as metal. Okay. So I think we got everything we need. We just set it up. This is the Q of the metal plus the Q of the water. And again, be consistent. We're ignoring the calorimeter. Now, if you were doing this for real, you'd have another term out here for calorimeter. So the Q of the metal is this unknown times this many grams times the temperature change. Final minus initial. And then we add the water term. And so we got the 4.18 for the water. And we got mass of water is 120 grams. And then the temperature change is 24.5 minus 21.6. There we go. Okay. This is the same type of calculation as before. We should get, well, I guess I better do it. I'm going to do this whole term right here. 24.5 minus 21.6 is a positive 2.9 times 120 times 4.18. So that's this term right here is 1454.6 joules. Positive. And this one, we need to do that 24.5 and minus 95.2 is minus 70.7 times 45.9. So this term is a minus 3245.1. So this is going to be minus 3245 times S plus this one. So I'm going to get rid of all the negatives. So let's move this whole term over on this side. Make it a positive. 3245.1 times S for the metal. And that's equal to 14.5, excuse me, 1454.6 on this side. So S is just this one divided by that one. Which is 0.45 joules per gram degree C. So what's 0.45 of iron? Okay. Now, why did they put that? Should be an equal sign. That's not a negative. That's equal. That's equal. Specific heat doesn't make sense if it's negative. All right. And 28 coming up. So you take 295.5 grams of a solid at 30 degrees and let it melt in 425 grams of water. The water temperature decreases from 85.1 to 30. Calculate the heat of fusion of this solid. Okay, what we're assuming is the heat of fusion is the amount of heat it takes in joules for the phase change to occur of a certain mass. And it's not a change in temperature. It happens at a constant temperature. So they're making that point here. The water went from 85.1 to 30, and the solid was already at 30. So the reason they're saying that is because the temperature has to be constant at 30 degrees in this case. They're saying that the melting point is 30 degrees. Okay, this is way hypothetical, right? In the real world, I don't think you could get away with this. But here's what we got. 295.5 grams of the solid. So the mass is 295.5 grams. And its initial temperature equals 85.1. No, it's 30, excuse me. It's at 30 degrees, excuse me. It is 30 degrees. But the water, this is the mass of the whatever, and this is the water. The mass of the water is 425 grams. Okay, now the water does change temperature. Its initial temperature is 85.1. And its final temperature is the same as the solid, which is now a liquid. Okay. Let me see if it'll work this way. So the heat required, the heat of fusion for the solid plus the heat change for the water should be equal to 0. All right. So let's leave this one intact and just solve for that one. So we're gonna put our values in here for water, 4.18 for the specific heat of water, and then the mass, grams, and then the temperature change. So final is 30 minus 85.1. Okay, so this value plus this value should be equal to 0. Let's see, 85.1 and 30 is minus 55.1 times 425 times 4.18, which is, what are our values? Our values in joules per gram. It's a big number. Okay. I get minus 97,885 joules. Okay, so the Q of fusion would be this value, positive that value, right? Just move it over here. Now it's a positive value. So this is the amount of heat that was absorbed by that mass. And the heat of fusion is in joules per gram because the temperature doesn't change. So we'll take this one and divide it by the mass, 295.5. And I get 331 joules per gram. There it is. Okay. One thing I forgot to do was ask you guys if you had any one of these specific problems. Yeah, you wanted to work on. I want to do that first before we run out of time. Were there any that gave you a particular heebie-jeebies? No? Okay. So we shall continue. Let's see. We did that one? Yes, we did that. How about this 32? In the lab, you mix two solutions, each originally at the same temperature, and the temperature of the resulting solution decreases, which is the following is true. So we went from an initial temperature down to a final temperature. Temperature decrease when we put these two solutions together and they were at the same temperature. The chemical reaction is releasing energy. Actually, release energy and get colder. It can't happen. This is an endothermic process. The chemical release is equal to no, not necessarily. Because we didn't have a, but we don't know the mass. We don't know the temperature change. Let's hold B in reserve, just in case. Chemical reaction is absorbing energy. That's true. This is endothermic. Okay. So that C is true. The chemical reaction is exothermic. No. So the energy release is equal to energy release is equal to S in delta T. No, actually, there are two things going on here. I wonder if that's true. The energy released is equal to S times M times delta T. You mix two solutions and the temperature decreases. So if the temperature decreases, final is lower than initial. So that should be a positive value here. You know, that could be. B could be a valid answer to more than one of these. Any arguments? You gonna take my word for it? Real scientists don't do that. We hammer each other.
I believe you.
We try to hammer the opposition into the dust to advance our careers. Let's think about that one. Energy released is equal to specific heat, which is essentially this, we're talking about aqueous solutions. And then the mass of both solutions and a change in temperature. Chemical reaction. You know, it could be E. Right? So be wary in case one of these shows up on exam.
What if this one does? And we pick C. Would you count that wrong?
No, because it's in there as C in the problem set.
But if we pick E, then you count it right.
That'd be right also.
Okay.
Yeah.
Gotcha.
But if I'm grading pretty fast, so if I skip over it and mark it wrong, call me on it. Okay.
Gotcha.
36. Exactly 123.7 joules will raise the temperature of 10 grams of metal from 25 to 60. What's the specific heat of the capacity of the metal? This is a very simple calculation. You just solve for the unknown, right? S equals Q divided by M delta T. So what's the amount of heat? 123.2. 7 joules. The mass, 10 grams. And then the change in temperature is it went from 25 to 60. So it's 60 minus 25. And you solve that equation, right? Joules per gram degree C. Those are the right units of measure. It should come out 0.353. Let's see, this would be 35. So it'd be 350. Yeah, it's about a third. Okay. Let's see, 38. On a cold winter day, a steel metal fence post feels colder than a wooden fence post of identical size because. Why would it feel colder? We sense temperature change in the nerve endings in our fingers. That's assuming you don't have water on your fingers, you just grab it and it sticks, or you don't test it with your tongue. So if the temperature changes more, it's going to feel colder to our, this is partly a physiology problem too. If it feels colder, that means the temperature changed more. So if the temperature changes more, that means the amount of heat that it absorbs causes a greater change in temperature. Right. So if we're comparing the heat capacity of wood to the heat capacity of metal, okay, this would be so many joules per gram degree C, both of them, joules per gram degree C. But this one is bigger. Right? This is, we'll just make up a number. This is say 1 and this is say 0.5. Okay. So if this is 0.5 joules per gram degree C, then if we're extracting heat, or if the object is extracting heat from your finger, the same amount of heat would cause a smaller change in temperature for wood than it would for metal. Correct? Okay. So it's based upon the difference in specific heat. The specific heat capacity of steel is lower than the specific heat capacity of wood. That's it. Okay. I'm gonna stop talking about my head on that. 43. Here's our old friend again. We're burning ethanol. Seems like a waste. When 21.1 gram sample of ethyl alcohol is burned, how much energy is released as heat? Okay. So I think I better put the equation up here for this one. Plus 3 oxygens yields 2 CO2 plus 3 waters. And the enthalpy is negative 1.37 times 10 to the third kilojoules. That's kilojoules for this reaction as written. So we can say it's kilojoules per mole of this because there's only 1 mole in that balanced equation. 21.1 gram sample would be what? 21.1 grams. We need to know moles because this is in terms of the reaction. How many moles are in the reaction? We need to know how many moles of that. 46.6 grams, 0.07, excuse me, grams per mole. Okay. So we need to find, that'll tell us it's about a half a mole, a little less than half a mole. 21.1 46.07 is 0.458 moles of ethanol. That's my abbreviation for ethanol. So how much heat is released? Well, if we can put that in terms of 1 mole of ethanol, that's what that means. 10 to the third kilojoules per mole of ethanol. Right? Because that's for the whole reaction, but there's only 1 mole here, so we can say that. Then all we have to do is multiply this times 0.458. That should give us the amount of heat in kilojoules. And the answer is in kilojoules, so that's good news. 1.37 times 10 to the third. And there, voila. 3 significant figures, 627 kilojoules. Or 6.27 times 10 squared kilojoules. There we go. Matches there. Thank you. I like this board better than mine, than the one in the other room. This one erases better. Okay, 45. We're on time. We got 10 minutes left. Total volume of hydrogen gas needed to fill the Hindenburg was 2.11 times 10 to the 8th liters at 1 atmosphere and 24.7 degrees. How much energy was evolved when it burned? Okay. So if the combustion reaction is this one, plus half an oxygen yields water, and the delta H is negative 286 kilojoules. We need to find out how many moles of hydrogen that represents, because this is in terms of kilojoules per 1 mole. So how do you do that? You forget the gas chapter already? PV equals nRT. This is a state situation. We don't know how we got there. So pressure is 1 atmosphere. Volume is in liters, that's good. 2.11 times 10 to the 8th liters. Moles is our unknown. I'm gonna go ahead and bring these two over here. R 0.08206 liter atmospheres per mole K. And the temperature needs to be in K. 24.7 plus 273. There we go. That'll give us the number of moles of hydrogen in that, actually in the dirigible, which is got a bunch of bags in it. Okay, so 2.11 exponent 8 and 0.08206 divided in 4.7 and 273, and then divide that into it. So I get 8.6372 times 10. Let's see. 1, 2, 3, 4, 5, 6, 10 to the 6th moles. So if this is minus 286 kilojoules per mole based on this equation, then we just need to multiply this one times that one. And I get 2.47 times 10 to the, I don't have my scientific notation plugged in here, so I have to count 1, 2, 3, 4, 5, 6, 7, 8, 9 kilojoules. There it is. Okay. Everybody bored yet? Maybe I need to make some more mistakes. Keep going. All right. Let's see, how many more do I have? 46. It's the next one. Based on the above action, what energy change occurred before we control? Okay, 46 is similar to the one we just did. So I'm not going to spend time on that. 51. I think we can do the 51 without a whole lot of calculating. We're just comparing specific heats. So if you have the same mass of each sample, the same mass of each sample, and they're all the same initial temperature, and you heat them with the same amount of heat, which one will have the highest temperature? Well, the same amount of heat will change the temperature the greatest for the one with the lowest specific heat. It can't absorb the same amount of heat for the same temperature change. If you put the same amount of heat into say lead versus magnesium, then the lead's going to have to change a greater degrees in temperature, right here, in order to match the amount of heat that was put into the magnesium. So the one that will have the highest temperature is lead. It has the lowest heat capacity. It can't hold the same amount of heat for the same temperature change as magnesium, or any of the others for that matter. Yeah, 145. Okay, let's see. Calculate the delta H for the reaction below. Okay. All right, notice what we're dealing with here, number 59. What does each one of these mean? Well, it can't be the heats of formation, right? Because the heats of formation always make 1 mole of product. Right? So it can't be heat of formation. These possibly could be heats of formation because these are elements. No, that one can't be, because that's a compound. So the only way we're going to get to this answer is with Hess's law. We've got to rearrange those equations to make this one, and then do the appropriate changes to this one, to each one of these, before we can add them together and get the final answer. Now, let me see if I've got what else. I don't want to miss doing an important one. We can come back to that. Yeah, okay. Let me hold 59 in reserve. I may have to do that one afterwards. Let's see. 68. Choose the correct equation for the standard enthalpy formation for carbon monoxide. Okay. Remember how you write the equation for the heats of formation? You start with the product, 1 mole of the product, and then you work your way backwards. and you take each of the elements in their most stable form. So this is going to be carbon graphite plus oxygen gas. Okay. Now, then you use coefficients here, fractions are okay to get 1 mole here. So that means we need a half here, 1 there. So this is going to be, and the delta H is a negative 110.5. Right, so it could be D, C, B, or E because these are all graphite, but we only need 1 of them, so it's only 1 of these. And this is the only one with a half an oxygen, making this one, and that's a gas. Carbon monoxide is a gas that it's most stable. Okay, so it has to be this one right here. Right there. Oh, I didn't write the number. This is 68. Okay. One of the main advantages of hydrogen as a fuel, this should be fairly simple. If hydrogen is going to be a fuel, what is it most likely to be the chemical reaction? It's more than likely going to be a combination of hydrogen and oxygen yielding water. So, there we go. So, what's the advantage? The only product of hydrogen combustion is water. Okay, we found our answer. That's the advantage. And as long as you have a plentiful, cheap, non-polluting source of energy, you can make all the hydrogen you want because this is the water planet. You can split water all day long and make hydrogen gas like crazy. As long as you have a cheap source of energy, that's the key. And at this point in our civilizational development, nuclear is the only way to go because the rest of them produce greenhouse gases. 79. Which of the following is not being considered as an energy source for the future? Okay. This is sort of a trick question. You can use any of these for energy as long as you can burn them. We can burn ethanol, we can burn methanol, we can burn oils. You can't burn carbon dioxide. Carbon dioxide is an end product. Now, we haven't discussed oxidation states yet, have we? We talked about oxidation states, redox reactions. I don't think so. Okay. So that explanation is for the future. We'll come back to it. Okay, that was 79, which was E. Okay, yeah, I'm out of time. Oops. Gas absorbs 188 joules of heat and then performs 310 joules of work. Change in internal energy. Okay, this is quickie. Internal energy is Q. I do that. Q plus W. So if the gas absorbs heat, this is a plus value, right? And if it performs work on its surroundings, that's a minus value. So we just have to subtract those two. Actually, add this one to a negative, which would be 1. Mm-hmm. 122.
Negative.
Negative. Yes, that's a negative. Hope that's the last. Oh, okay. Calculate the delta H for this reaction. Okay, now this one will be simpler. These are all heats of formation. Okay, so you know how to do that. I'll come back to it later. Assuming Ms. Farrar doesn't come in here and steal my room while I'm asking. Okay, so I'm going to leave this up here and come back and do those after the lab. All right, we're going to back up and pick up number 59. This particular problem is an exercise in Hess's law. The reason we can use Hess's law, which says that the target equation, in this case, here's our target equation, can be compiled by manipulation and addition from a number of other equations that have their enthalpies established. And if we follow the rules, and then at the end, we can add the enthalpies of the individual reactions, and that will be the enthalpy for this overall reaction here. Okay, so here's what we have to do. The best way I find is to write out the target equation first. So we'll put it at the top. So this is P4O10, that's a solid. And when you're using Hess's law, sometimes it's important to know what the phase is, because some phase changes are incorporated in the reactions. And you need to know what the phase is, because there will be an enthalpy associated with any phase change as well. So we're going to include the phases just to be careful. And this is chlorine gas yields 4PCl3. Oh, no, it's not. That's not the target equation. 6PCl5 gas yields 10CL3 PO gas. Okay, that's the target equation. The best way I found to solve this problem is to work backwards. In other words, we know that we need these things in our final equation. So then we look at the given elementary equations and see which ones provide the information we need. Here is, we can start from here, P4O10. Which one has P4O10 in it? It looks to me like Roman numeral 2 has P4O10 in it. So it's P4 solid plus 5O2 gas yields P4O10 solid. And the delta H for this is minus 2967.3 kilojoules. Minus 2967.3 kilojoules. There. Okay. In order to use this one, this P4O10 is 1 mole, and we need 1 mole. But it's on the wrong side of the arrow, so we have to flip it. We have to write it this way. P4O10 yields P4 solid plus 5O2 gas, and that makes the delta H now change the sign. When you run a reaction in the opposite direction, you just change the sign of the enthalpy. So this one is 2967.3 kilojoules. Okay, So we've taken care of that one. And we're going to use this equation. Okay, what about PCl5? Which one has PCl5 in it? Let's see, PCl5. Here we go. There's PCl5, and it's on the wrong side. So as written, Roman numeral 3 is PCl3 gas plus chlorine gas yields PCl5 gas. Okay, just checking my numbers. All right, and the delta H for this one is negative 84.2 kilojoules. All right, so this one has to be on that side, plus we have to multiply it by a factor. So if we invert it, PCl5 yields PCl3 plus Cl2, and the delta H for the inverted equation is positive 84.2 kilojoules. This is a positive also. But now we need to multiply by the factor. We need 6 PCl5s. So I find the best way to do that, to be sure that we get it all together, is put a bracket around the enthalpy also. You're going to multiply everything through by a factor of 6. So now we have 6 PCl5 gas yields 6 PCl3 gas plus 6 Cl2 gas, and the delta H is equal to plus 6 times 84.2, which is 505.2 kilojoules. Okay, so now this one, this equation takes care of that one. Okay, how about the Cl3PO? Which one has that in it? Cl3PO, here it is, Cl3PO, right there. It's on the correct side, but there's not enough of them. So let's write that Roman numeral 4 equation, which is PCl3 plus 1/2 O2 yields Cl3PO gas. The delta H for this one is negative 285.7 kilojoules. There. Okay, we need 10 of those. So we've got to multiply this whole thing through by 10. That gives us 10 PCl3 plus half of 10 is 5 O2. And then 10 Cl3PO. There we go. And the delta H for the reaction now is 10 times that, which is negative 2857 kilojoules. Okay, so that takes care of this one if we use that equation. Okay, so we've got these 3 equations. The question is, when we entered these equations, these 3 equations, did we add anything that's not in the target equation? If that's the case, then we got to see if they cancel out when we add them together. So here we have, I'm going to keep that one, P4. P4 here? No, there's no P4. So this one, we need to use the last equation to get rid of that P4. This P4 is on the right, that P4 is on the left. So we're going to use equation number 1, which is P4 solid plus 6 chlorine yields 4 PCl3. And the delta H for that one is equal to minus 1225.6 kilojoules. Okay. By the way, if we're going to use this one, I better identify it over here also so I get the right numbers. I'm going to use this one and then this one. Okay. Now, we've taken care of the P4. Right, so it's here, there's that P4, here's the other P4. Those will cancel because they're on opposite sides of the arrow. How about the 6 chlorines? We don't have any chlorines up here. The Cl3PO. So 6 chlorines here and 6 chlorines here on opposite sides of the arrows. So those cancel. And we have PCl3, nothing there. PCl3 here. So this is 6 PCl3 and 4 PCl3 on the right-hand side of the arrows. And on this side, we have 10 PCl3s. So these 6 and those 4 cancel these 10. These 10 are on the left-hand side of the arrow. These are both on the right-hand side. So they cancel. Okay? Now, just because we cancel this one, this one, and this one, doesn't mean that we can throw this away. We have to keep that because this reaction is still part of a total. Okay. So we're going to use that one, that one, that one, and that one. Let's see if we've got everything we need now. Okay, there's P410. Oh, there's 502. 502. There must be some O2 around here. Okay, here's an O2. Here's an O2. Here we go. There's 502. And there's 502. They cancel. Okay. So we got this one taken care of. PCl5, 6 PCl5, yes, we need that one. The rest canceled. And we need 10 Cl3PO. There. Okay. Now let's check. Have we counted for everything? Those cancel. Those cancel. We need that one. We need that one. Cancel, cancel. We need this one. Cancel, cancel. Okay. So we've accounted for all of them. And the only ones that we have left are part of that equation. Now, we know that if we add them together, they will give us that equation. So now what we want to do is this one also, is add these delta H's up. This one, that one, and that one. So 2967.3. And then positive 505.2. And then negative 2857. And negative 1225.6. And I get the total here, the delta H for the overall is equal to minus 610 kilojoules. So the closest one to that, well, actually, I do have a 0.1. I just threw it away. 0.1 kilojoules. So there it is, right there. That's a lot of work. to get the answer. But you have to be methodical about it. Very, very rigid in your assessing what's needed and how to cancel them out. All right, so that's 59. Now we want to go one more. One more that I need to back up and get. So let's erase this. This. Okay. Uh-oh. What happened? Oh. Screensaver. There we go. So now we're going to go back to number, well, I'm going to go ahead to number 99. Let's see if I can get there without having to manually attack the computer. And almost. I got one answer down there that doesn't show up. Let's see. All right, we'll get it if we need it. All right, so this one says nitric acid, HNO3, was first prepared 1,200 years ago by heating naturally occurring sodium nitrate with sulfuric acid to produce sodium bisulfate and collecting the vapors, which are HNO3. Most of that is fluff. The important part is here. Calculate the standard enthalpy for this reaction. Sodium nitrate plus sulfuric acid yields sodium bisulfate plus HNO3, which is hydrogen nitrate, right? It's not in solution yet. So we don't call it nitric acid. They call it nitric acid, I think. But until you put it in solution, in aqueous solution, it's not acid. It's hydrogen nitrate, gas. Okay. So to calculate the standard enthalpy for this reaction, we can use the heats of formation right here. Heats of formation. So for this reaction, I'm going to write it up here. Sodium nitrate solid heated with sulfuric acid. This is liquid, so that must be 100% sulfuric acid, which means it's not sulfuric acid, it's hydrogen sulfate, HSO4, solid, plus HNO3, gas. Okay, before we can do anything, what we need to do is be sure that this equation is balanced, because the coefficients enter into the calculation here. So let's be sure it's balanced. One sodium, one sodium. One nitrate, one nitrate. One sulfate, one sulfate. Two hydrogens, one there and one there. That equation is balanced. And the coefficients for each one is 1. Now remember when we calculate the delta H? The delta H for the reaction. Just back up like this. The standard enthalpy for that reaction is equal to the sum of the N times the delta H's of formation for the products, okay, and minus the sum, and these N's are coefficients. In our case, they're all ones. which is convenient, a formation for the reactants. Okay, so how about sodium? Let's do the products first. Sodium bisulfate is minus 1125.5 kilojoules per mole. So minus 1125.5 kilojoules. And since there's only one mole of them, that's kilojoules. Okay. Then we want to add the next one, which is HNO3. Keeps the formation for HNO3 is minus 135.1. Minus 135.1 kilojoules. Okay. Then we subtract the reactants. Sodium nitrate, right here, minus 467.8, minus 467.8 kilojoules. And then add to that H2SO4, which is minus 814, minus 814 kilojoules. There we go. Okay, so that's the hard part. The rest is doing the calculations. That one's going to be 1125.5 and 135.1. Change the sign. This is minus 12. Fix that. 1260 kilojoules. And this is going to be minus whatever this is. 467.8 and let's see, let's change sign. And then 814 minus. So this is minus 1281.8 kilojoules. That's a minus of a minus. So this is a positive. I just changed the sign. Let's see. Yeah. And then 1260. Change the sign and add it together. So the delta H for this reaction is 21.8 kilojoules. It's a positive value. Okay, I was close. 21.2 is the best answer. It's closest to 21.8. And E does not say none of the above, I don't believe. Right. Okay. So in this case, we have to pick the best answer. I could have made a calculation error here. Could be a rounding error. But this is the best answer. Okay, that's it. That's it for our review for exam number 4 on chapter 6, I believe.